Hello SolidWorks users. First of all, thank you very much for tuning in today. We are about halfway there into this user group meeting, and I am super excited to be here with you. Not just because I have an exciting presentation coming your way, but we are going to talk about simulation. Yep, you heard me right. You may have got a little sneak peek about this through Jordan's presentation, but I am going to take a deep dive into this topic today through my presentation. I highly encourage you to engage with us through the live chat section and ask us any questions that you may have. So, that being said, welcome again. My name is Shreyas Vaidya. I'm an industry process consultant here at Dassault Systems. I work with Ramesh Lakshmipati and North American simulation team and support our 3D Experience Works simulation portfolio. So, what's the agenda here? Before we look into it, I would like to give you a quick recap. So our team is designing a limo style race car. Heading the chassis department on the CAD front is our very own Jordan Terry. Most of you may have seen his presentation a few hours ago, but for those of you who are tuning in now, Jordan is one of our very best when it comes to CAD. Well, I would have called him the CAD god, but unfortunately that title has been given to Andrew Barnes by Jason. So I'm not gonna mess around with that. Anyways, enough joking around, folks. So we started off with a preliminary design for the chassis based on the tire and the suspension data provided to us by Andrew. Then Jordan came up with a really good structure based on our requirements. So the goal for me was to analyze this chassis, the structure for how stiff it is. Can it handle the stresses from a certain force? Can it stay within the permissible elastic deformation limits? And similar other results. And then convey all this back to Jordan with some recommendations that might help improve our new design. So the entire workflow is something that I plan to cover through my presentation today. Starting off, we'll explore simulation results from Jordan's initial design, based on which I have sent Jordan a message. This message includes some design recommendations for the new design. You may have seen it in his presentation. Then Jordan got back to me highlighting the changes that he made, and we will be taking a look at that message. After this, I'll walk you through some of the key steps in setting up this model, and we'll also explore some key results from the simulation. We'll take a look at how these results can be interpreted and also how we can export the displacement plot data into an Excel workbook. We'll then use this data in an Excel program that I created to plot the torsional stiffness curve. Finally, I'll show you the workflow that integrates SolidWorks with the 3D Experience platform. To demonstrate this, I'll make a quick change to our design and save it as a new revision that can be later used for analysis on the platform. Okay, let's get this started. So we are going to design a space frame chassis for our car. What is a space frame chassis, you may wonder? Well, it is a type of chassis that is fabricated from joining multiple tubes. The commonly used cross sections for these tubes are circular and square. Now, we are not going to go into much detail about this type of chassis, but the important thing to know here is the stiffness is the most important characteristic of these type of structures. Now, the goal for us here is to improve the torsional stiffness, reduce the weight, and also keep the center of gravity as low as possible. All this will ensure that the car will have superior handling and performance. So what you see on the screen is a stress contour plot from our first design iteration. So you can obviously notice there are a few hotspots on some of the members and some of the nodes as well. And in addition to this, the way we are applying force is at a location where the spring and damper is going to connect on the chassis, on the front left wheel, which happens to be somewhere on this member. And you can obviously notice that there is no node connection at the point of application of this force. So these are the couple of changes that I am going to recommend to Jordan as we build on our first design iteration. So I sent out a message to Jordan recommending some changes. You may have seen it in his presentation, but in case if you missed Jordan's presentation, here's the message for you. Hey Jordan, how's it going? I wanted to reach out to you, tell you that I ran some simulation on our first design iteration and the results look pretty great. I think we have a really great first design that we can build on. Though I also have some recommendations based on the simulation results that I feel can be a great improvement in our second iteration. So let me quickly show you a couple things. So the first thing that I definitely would like to see is if we can add a few cross members, if we can create that load path for the forces to um, transfer laterally and also longitudinally along the chassis, that will be great. I definitely saw a few hotspots on particular members or on particular nodes of the chassis in our first iteration. So um, I think we should definitely try and avoid that. The second thing would be if we can just taper out the side impact structure of the chassis and then on the top side and just taper in it on the bottom side. Also leaving some clearance for all the ducting, wire ducting and things like that. I think that'll be great. Um, and then if we could, add a fillet and avoid that sharp edge, that sharp corner on the roll cage structure, I think it will distribute the stresses more evenly there as well. So yeah, these are just a few things that I noticed from based on the simulation results. And I don't know, let me know what your thoughts are. I think I'll definitely run a new simulation if we get these changes and then see how it goes from there. Thanks, Jordan. Thanks a lot. I'll talk to you soon. Bye. Okay, let's see what Jordan came back with.
Hey Shreyas, thanks for your video voicemail. I've received all your recommendations and I've implemented them. In fact, here's the model right here. You can see that I've added a lot more cross members. If we take a look at this side view, uh, I've zigzagged this cross member pattern across the frame, made the roll cage a little bit more robust, and added that round to the front of it like you said. I also brought down this little area right here, maybe giving the driver some more arm room. So check out how that might affect your simulation studies, and hopefully it keeps it just as robust or more. Another thing that I did to strengthen things up is on the top of the roll cage. I added some cross members as well. So I figured, hey, if we're rolling this thing over, we want to make sure we keep that driver's head safe and secure. The final thing that I did over here on the front view, or actually let's go to this view right here. You can see that I've tapered in the bottom half of the frame for that side impact load, and also to open up an area for our cabling and ducting for our wires and electrical lines. So I think we'll have plenty of room for that. Hopefully the side impact will be even stronger. And I don't know. Let me know. Hopefully all these changes are in the right direction, Shreyas. Thanks for your guidance. And we'll talk very shortly when you get the rest of the results. Take care.
All right. So now that you all have an insight on how Jordan and I went about making these design changes, let me explain you the workflow I followed to set up the model for determining the hub-to-hub torsional stiffness. The setup is similar to a typical test rig that you may have seen. On a test rig, what usually happens is you clamp one end of the chassis and twist it about the other end. The twist can be accomplished either through the application of a torque or by applying a bump force on one of the wheels. Now, in my case, I'm applying a bump force of 2.5 Gs on the front left wheel, which approximately comes out to be 1767 Newton on a nodal point on the chassis where we are going to connect our spring and damper system. Now, what this force will do is it will twist the chassis along its length, and the direction of this twist is shown by the arrow in the bottom left corner on the screen. Now, let me walk you through the setup process and also show you some tips and tricks along the way. So, the setup process that I'm going to show you is on the design that we think is going to be our final iteration. Now, the starting point for me is really the point where I get the design from Jordan. Now, the important thing to note here is I'm only going to perform a 1D static analysis on this frame. So what I really need from Jordan is just a 3D sketch, and I'm all set to set this model up. So the first step for me is to get this component from SolidWorks onto the 3D Experience platform, because that's where I'm going to perform my analyses. Now this step is super simple. From the SolidWorks connector that is inbuilt into your software, all you have to do is select the component, click on the compass in the top left corner, and select the appropriate app that you wish to open this file onto the 3D Experience platform. Now in this case, I'm going to set this model up using the mechanical scenario creation application on the platform. Okay, we are now on the 3D Experience platform and in the mechanical scenario creation application. I have already set this model up before this presentation started and would like to use it to discuss the setup process. But what now? Remember, we only got the 3D sketch on the platform. We don't have any cross-section data associated with it. So how does the software know what exact cross-section these beams are made of? Well, honestly, it does not, unless you specify something. So that's the first thing I have done. I have created different profiles, and then what I do is I apply these different profiles on individual members of the chassis. So for example, I have created a beam profile of 1 inch outer diameter and 2.4 millimeters thickness, and then I'm applying this profile to the main hoop on the chassis as seen in the graphics area. This beam section has a material associated with it, which is SAE 4130. In addition to this beam profile, I have created some other beam profiles with mostly 1 inch outer diameter pipe with 2.4 to 1.6 and 1.4 millimeters of thickness. I also have a profile with 15 millimeters of outer diameter and a thickness of 1.6 millimeters. Now, all of these profiles have been assigned to specific members on the chassis, as you can see here in the graphics area. Now, the next step for me was to create a mesh on this model. We create a mesh to discretize the model into finite elements. Now, I'm using a mesh size of 4 millimeters and a tolerance of 0.1 millimeters to mesh this model. So, a quick recap. We have created the beam profiles, we have assigned the materials, we also meshed this model. What's our next step? What should be our next step? We have to twist this chassis in such a way that we can study the stresses, study the displacement on different nodes and different members, right? So that's what we are going to do. We're going to start off by creating some restraints and then are going to apply a certain load on a specific location on the chassis. So for this, I have created a clamp on the rear suspension pickup points. So basically what I'm telling the software to do is I'm giving it a few points, which are basically where all the suspension components, rear suspension components connect with the chassis. And I'm telling the software to clamp all of these points. In addition to this, I am applying a bump force of 2.5 G at a point where we are going to connect the spring and damper system on the chassis at the front. So there are several critical points on the chassis. These are the points where I wish to study the stresses and displacement in much more detail. So what I have done is, before solving this model, I have created some geometric groups. Now, these geometric groups consist of all these critical points. Now, the benefit of doing this is when you're studying a specific contour plot, you can request output on these geometric groups. This way, you can study all the critical point at once. Okay, so those were some key steps in setting up this model. So what I did was I went ahead and solved this model using 12 cores on my local machine, and it was pretty fast since it's a static analysis problem. It took around about a few seconds. But let's say if you're working on a really complex problem, something like a crash simulation or a drop test, which is an explicit analysis case, you also have the option to solve it on the cloud. And when on the cloud, you get the maximum number of cores that you get is 144, which can be very fast when compared to your hardware specifications in some cases. So just wanted to throw this out there. But yeah, let's go ahead and take a look at some key results. So what you see on the screen is a stress contour plot. To start off with, you can really point anywhere on the beams and you'll get a stress value. This is a very interesting feature. But I'm also interested in knowing the location of this maximum stress point on the chassis. So we can obviously determine from the legend here on the right hand side that the maximum stress induced was 141 megapascals. But I'm more, as I said, I'm more interested in knowing the location of this maximum stress point. This will help me better iterate my further designs if that is something I'm looking for. So for this, I'm going to click on show minimum and maximum values and then switch to maximum only. So this will give me the exact location of the maximum stress that is going to be induced. Let me turn this off real quick so that we can move on to our next result. Now, if you want to turn the geometry on, in our case, it's a 3D sketch, you can do it from rendering settings. This way you can visualize your original geometry in this contour plot. You can also plot a section view using the plot sectioning option. To set a view, you can either rotate or drag the triad about a certain axis. I am now going to switch to the displacement contour plot. This is one of the key results for us. In addition to this, I'm going to request an XY plot from field. Now this XY plot will contain information for displacement for all the critical points that we have created. So for support, I'm going to select node sets and set it to critical points on the left side. Now my variable is set to translations and I'll set my magnitude to vector component 3, which is basically along the vertical axis, that is the Z axis. Now you see all the critical points are highlighted in the graphics area. These are the critical points that we have included in the group called critical points left. I'm going to say apply and you will see a plot which basically is a displacement versus time graph for all these critical points. The curves indicate their displacement with respect to point as the force is being applied on the chassis. So as I said, this data is very important to us. We'll need it to plot a torsional stiffness curve for the chassis. So what I'm going to do is I'm going to export this data into a format that is easy for us to get the values from. So to do this, I'm going to right mouse click the plot that we have just created from the design tree, click on export, and then set the type to Excel workbook, and then click apply and then OK. So this is the Excel workbook that we get. Now, how do we read this? Well, to start off with, node 33 will have a maximum displacement of 3.44187. Similarly, The maximum displacement of all the 21 nodes, 21 critical nodes that we have specified is going to be in this Excel workbook. So all I have to do is copy these maximum displacement values and then paste it into a Excel workbook that I have created, a program that I have set up in an Excel workbook to calculate the torsional stiffness of the chassis. So as you can see, these are all the maximum displacement values of those 21 critical nodes that I brought from the data that we exported into this Excel workbook that I have set up for calculating the torsional stiffness. So torsional stiffness is nothing but the torque required to produce a unit angular displacement. Since we know the displacement, the vertical displacement of these critical points and also their respective distances from the center plane, we can calculate the degree by which these critical points were displaced. And since we also know the force and the location of the force that we have applied, we can calculate the torque that was required to produce these respective angular displacements. And that will give us the torsional stiffness for each critical point. Okay, so now that we have calculated the torsional stiffness for all the critical points, let's see how our stiffness curve looks like. We have plotted these stiffness values on the y-axis, whereas on the x-axis, we have the location of these critical points about the length of the chassis from front to the rear. Now this curve represents the increasing torsional stiffness of the structure as we go from the front to the rear. The y-axis value of this curve corresponding to the x-axis value of 0 will give us the torsional stiffness at the front axle. So the torsional stiffness at the front axle comes out to be 2450 Newton meter per degree, which in layman's terms means it will require a torque of about 2450 Newton meter to displace the structure by 1 degree at the front axle. Now this curve, along with the data from the displacement and the stress plots, serves as a great starting point for a new design iteration. We build on Jordan's first iteration of the chassis by studying these KPIs. Okay, what if this is not your last iteration? What if, based on the simulation results, you think you can make further design changes to make the structure more stiff or let's say make it more lighter? In that case, what would be the most efficient way to make these design changes? It is just not feasible to start from scratch, right? Especially when you have made so much progress. Well, let me show you how you, or really anyone who is working on this design in SolidWorks, can make a new revision and push it back onto the 3D Experience platform for further simulation. So what you see on the screen is a one mice stress contour plot. You basically see the stresses on different nodes, on different members of this chassis, right? So what I instantly notice is these top crossbars doesn't really encounter a lot of stress. There's this very less stress induced in this cross bars at the top. And what this really it is doing is it's not only adding to the weight of the chassis, but it also adding to increasing the center of gravity of the chassis because these bars sit at right at the top of the chassis, and all it is doing is increasing the center of gravity slightly. So do we really need this? So what we are going to do next is we're going to go back to SolidWorks and remove these crossbars and make a new revision and see how the new simulation behaves. But my focus will be on showing you that workflow of making the design change, making a new revision. So let's take a look at that. Okay, so we are back in SolidWorks. Now the first thing you may want to do here is to reserve this file. Okay, and the reason being, it as the name suggests, it is going to reserve the file for you. And let's say if anyone else has access to this file, they won't be able to make any changes to it as long as it is reserved by you. So that's basically what we are going to do. So to do this, all you have to do is you can right click on the file in the 3D Experience task pane or the connector, and reserve it, or you can also do this from the action bar. Make sure you select the file and then click on reserve. Okay, so uh, and the way you know that the file is reserved is from this green key icon here in the top. So now our goal is to make a new revision from this file, and then we are going to, as I said, we are going to build on this current design iteration. We are going to make further changes to it. So in order to make a new revision, what you can do is you can select the file, and from the action bar here at the top, you can say new revision, make new revision of the file. So you'll see this dialog box. It says, okay, the current revision is D.1. The new revision, the software is going to call E.1. If you want to add uh, any comments, so in this case, I'm going to say removing crossbars at the top. So yeah, that's pretty much it. You can keep it simple, and I'm gonna say let's revise this. I'll give it some time so that it saves. And what it does is it automatically converts into a file format that is 3D XML file format, which is more compatible with the platform. So it did convert the file, and now it says that okay, a more recent version exists, and you're currently on D.1. So we want to switch to the more recent version, right? So what we can do is select this file and say replace file by revision. So a dialog box pops up and you see all the different revisions of this file. You see when it was created, when it was modified. But let's select the current file. Let's select E.1 that we just created, the new revision, and let's click OK. So notice how the revision uh, is changed here. Okay, we are again gonna give it some time. There we go. So we have the new revision now, but again, it is not resolved. So what I'm gonna do is I'm gonna select this guy and then click reserve. So now only I can make changes to this file. And let's say if Jordan has access to this file, he won't be able to make any changes since I have reserved this file. And as you can see, the green key is right here. That means this is the reserve process is complete. All right. So now what we are going to do is we are going to select this crossbar. I know it's sketch 3D sketch 18, so I'm going to select this. I'm going to say edit the sketch. Okay, instantly this is the status says that okay, the file has been modified in this particular session, and the current status is that you haven't saved this file. Okay, that's good. That's good to know. So I'm gonna select these crossbars. I'm gonna hit delete and then exit and save this model. Okay, so that's basically the change in this latest revision that I'm calling E.1. So I'll go back to the 3D Experience task pane, select this file, and then click on Save. So a good thing about this connector is, and as the name suggests, it connects your SolidWorks designs to the collaborative space on the 3D Experience platform. So any change you make is instantly updated on the platform. So you don't have to worry about um, saving your files on a local drive or on a flash drive, plug it in somewhere else, and then um, get that file onto the new PC and start working with it. It's all connected. That's the most important point to note here. Okay, so there we go. We have saved the file. The file has been converted as well. Before we move on to the next step, that is basically pushing this file onto the 3D Experience platform, and this time we are going to do it slightly in a different way than you saw earlier. But before that, what I would do is I would unreserve this file so that um, it's pre-open, and then if anyone wants to make any further changes to this design, then they'll be able to do this. Okay, so that's pretty much the workflow in SolidWorks. Now we are going to go to the platform and see how we can replace uh, this replace our previous design with the current revision that we have. All right, guys, we're back on the platform. Now, before I replace this current model by the revision that we have just created, E.1, what I'm going to do is I'm going to create a new revision of the physics simulation itself. So the current physics simulation I have is this. So really all I have to do is select the current physics simulation, and I'm going to search for collaborative lifecycle application from the compass at the top. So once I have this, I'm going to just select the collaborative lifecycle application, and notice how I'm in the collaborative lifecycle for the native apps right now. So the action bar kind of change. So as I said, let's create a new revision of the current physics simulation. So I'm going to select this physics simulation, and here from the lifecycle tab in the action bar, I'm going to click on new revision. So what I'm basically telling the software is uh, I'm telling it to clone this current simulation that I have, current physics simulation that I have set up, I have simulated, and then also the results as well. So I'm going to say OK. Okay, so it looks like the new revision was created and it has been opened in a new tab. So the earlier one was called C.1.1 A.1, and this one is called B.1. So it is pretty much the clone of the exact clone of A.1. Now, since we have everything set up in this simulation, it just doesn't make any sense to um, start from scratch working on the new design revision that we have. So that's what I wanted to show you guys. So what we can do here, what we can do at this point is, and let's also quickly recap what we have done up until now. I know this can be a bit confusing. So uh, we had some simulation results from the previous simulation that we done, and we found out that okay, we did not want those crossbars at the top. Those were just some those were adding to the weight and just increasing the center of gravity. So we went back to SolidWorks, made those design changes, created a new revision. We called it E.1, the design revision. It is important to note here that revising a design and revising a physics simulation are two different things. So we revised the design from D.1 to E.1. We came back on the platform. We revised our physics simulation from A.1 to B.1 that you see here on the screen. And now what we are going to do is we are going to replace the current model that you see on the screen, because if you notice closely, it still has those crossbars, right? Because the 3D part that we have, the model that we have is still D.1. So what I'm going to do is I'm going to right click model in the design tree, say replace model by revision, and then I see the list of all the 3D parts, all the different revisions, design revisions that I have created, and some other data associated with it. So, for example, E.1 is our latest revision, and if I can track this, I'll see the description associated with it. We said, okay, we are removing the crossbars from the top, or that are at the top. So all I have to do is select the revision that I want to switch to in this physics simulation, and then hit OK. So let's give it a few seconds. So what is it is going to do is, as you can see, the current revision is T.1. It's just going to swap it to the latest revision, that is E.1. You'll see a short message here, switch to edition is successful. And that's really it. I know you still see the crossbars here at the top, but a quick update will basically fix it, and then you basically have to simulate the model again. So we are not going to go through that process over again. We have already covered that. I just wanted to show you this workflow, how easy it is to, go back to SolidWorks, make those changes, come back here on the platform, and simulate the model again to study your components, your assemblies for the changes that you may have made. Um, so yeah, that's pretty much how the workflow is. So the benefits. What exactly were the benefits? What exactly were the main benefits from integrating a simulation workflow with an already existing robust design workflow? So to start off with, we were able to do multiple design iterations in a really short span of time. Now, this comes directly from some of our simulation results, some of our key simulation results that okay, we know, okay, these are some of the key areas that we need to focus on in our next design iteration. So as you saw how the workflow was very integrated, I was able to convey that message to Jordan. Okay, so these are some of the key elements that I want you to change. Uh, Jordan did that. We brought our geometries, we brought our structure back onto the platform. I simulated it again and basically let Jordan know, okay, so some of the changes that we made did really work. Some of the changes, we still have to look at some of the other changes that may or may not be there. But yeah, to start off with, that's definitely the most important thing that comes out of from integrating these two workflows. Now, the second thing I can think of is we're able to, as I said, we're able to build on Jordan's first design iteration and really take all those simulation results into consideration, and then ultimately we're able to improve the hub-to-hub torsional stiffness of the chassis, which is basically what our goal was to make it more stiffer, to make it more lighter, um, and to also lower its center of gravity would be the third one. So yeah, those are some of the top benefits that I personally notice that we had from working in a very collaborative environment through all these tools that we have, not just SolidWorks, but also the connector and also the tools on the 3D Experience platform. So that is pretty much it as far as the simulation workflow was concerned. In reality, the next step for us would definitely be to fabricate this chassis and physically test it for all the parameters that we have based our design iterations on. Okay, so throughout the presentation, you heard me saying structure solution on the platform, the structural mechanics engineer role on the platform, and things like these. So what exactly are these roles? To start off with, these roles offer advanced cloud-enabled capabilities powered by Abacus. Let's take a deeper dive into these four different structure solutions or roles, as we like to call them, that are available on the 3D Experience platform. So let's start with the structural designer role. This is an entry-level role that is mainly focused towards designers and engineers. Let's say you're someone who is looking to perform a simple linear static analysis on your components to study parameters like stress or displacement or even factor of safety, then the structural designer role is probably the best fit for you. This role will also offer features to perform a frequency analysis or even a buckling analysis. It also comes in with features that lets you set up a basic thermal simulation if that is something you're looking for. Now, the structural engineer role sits slightly higher in the tree than the structural designer role in terms of features and capabilities. Okay, this role packs all the features from the structural designer role, but in addition to this, it also comes in with features that can help you set up a linear dynamic study. So, if you are looking for this, structural engineer is probably a good fit for you. The next role is where we start to move into some really advanced capabilities. This role is called the durability performance engineer role. If you're working with advanced materials, something let's say like an hyperelastic material, or maybe you need advanced meshing techniques for local mesh refinements, the durability performance engineer role has the tools and the features to accomplish these needs. This role will also come with advanced contact detection tool, which will allow you to set up a contact property in case you have interacting parts during simulation. One example where this feature can be used is, let's say, in a crash simulation setup where there are multiple parts that undergo large plastic deformation and come in contact with each other. In addition to this role will also offer you features to set up a nonlinear static or even fatigue analyses. Okay, so now we have our flagship offering, which is called the Durability Mechanics Engineer role. This role will offer all the tools that the other roles has to offer. But in addition to this, it comes in with a geometry preparation tool and a material calibration app. And these are just the two applications that are additional to this role. The material calibration app can come in handy when you are trying to calibrate a material from scratch. Let's say you have a material test data from a lab and are looking to calibrate and create a new material from it. This app can provide you with all the necessary means to do this. The durability and mechanics engineer role also offers you robust features to set up a nonlinear dynamics simulation. So that was a very high level overview of the structure solution that we have on the 3D Experience platform. On the fluid side, we do have a role which is called as the fluid dynamics engineer role. Okay, this would be a good point to conclude my presentation, but I would highly encourage you to stay tuned for another exciting presentation, a simulation presentation that is coming your way. Omar is going to present on aerodynamics of this car using the fluid dynamics engineer role. So that being said, I would like to hand it back over to the race control. Thank you very much for tuning in. I hope you enjoyed the presentation. Take care and stay safe.